Now we get to the next piece of our program, which is our keynote by Phil Rathle. And I won't read this to you. I'll just say he is the Vice President of Product for Neo4j, which has nothing to do with what he's going to talk about other than that's the company he's from. He said a bunch of Swedish guys invented this, and who knows where the name came from, something about the Matrix and blah-de-da, I don't know. But in any event, he's going to talk with us about the various tools that are available in this place right now, which I think is a very fascinating thing to do, because we talk about the explosion of data with Internet of Things and everything else that's going on. Well, there's an explosion in the number of tools to address how to deal with all of that data. And so I look forward to hearing what tool do we use for what. Ladies and gentlemen, Phil Rathle.
Thanks very much. And thanks to all of you for being here. Thanks to Wayne State and Dr. Chinham and Provost Whitfield and all the rest. Yeah, last count, there were 320 databases out there. There's like another 2 coming out every week. So that makes all of your jobs challenging. Hopefully this conference can help elucidate some of that, and this introduction can maybe give you a framework for experiencing the next couple days. So as I said, these 2 days are about you, and I'm going to start by offering you a few things I hope you can take away from this particular session, but I think they correlate very well with what you have, what you'll be able to take away from the entire session. Number one is a viewpoint on what are some of the things that big data can offer you. Number two is understanding enough about the technology that you can start to gain a better perspective on how to evaluate the many, many technologies out there, the 300 plus databases, and that's just databases. You have ETL tools and BI tools and languages and so on. And then how that might affect your IT portfolio going forward. And then third, being able to reap some of these benefits, but also understanding what some of the pitfalls might be so that you can avoid stepping into them. I'd like to motivate from the McKinsey Global Institute paper released just 3 months ago called The Age of Analytics, Competing in a Data-Driven World. And I'm going to read these quotes because I think they're quite impactful. The first says, data and analytics are changing the basis of competition. What that means is that your competitors are using data and analytics to improve what they do and become more competitive, which means that you have an imperative to do the same. And so there's this game of leapfrogging that's going to start. And if you look at some of the companies I'll talk about later that have disrupted industries and created new industries over the last decade, those have been purely through the result of data and analytics. And this is pervasive throughout all industries. Another one is that leading companies are using their capabilities not only to improve their core operations, so it's not just incremental change, but to launch entirely new business models. So whatever business you think you're in today, maybe that's not the business you'll be in a couple years from now if you truly look at reinventing the opportunity. Here in Detroit, there's all this cutting edge work happening around autonomy and autonomous vehicles. Well, maybe that can transform into all sorts of other autonomous devices that aren't vehicles, as an example. And then the third is where previous titans of industry poured billions into factories and equipment. This is the industrial age and later part of the 19th and most of the 20th century. New leaders invest heavily in digital platforms, data, and analytical talent, which means the companies that are going to be around in the next 20, 50, 100 years are ones that today have already begun investing in technology as a core asset. I'm going to start with a cone. It's a quote from Søren Kierkegaard from nearly over 170 years ago, 1844. He said that life can only be understood backwards, but it must be lived forwards. I'm not going to argue with the second part, but I'm going to cause us to question the first part. Life can only be understood backwards was set in the context of tooling, technology, information flow of the day. And if we look at where we are today, the reason it wasn't possible 170 years ago to understand life forward is that understanding life forwards requires understanding this ultra-complex system that is the real world and all of the different causalities and variables, and try to project forward. And today we're in a very different spot. And I'm going to show you a great example from the real world, from one of my favorite short videos. This is a natural system where wolves were reintroduced into Yellowstone National Park, and you can actually see what happens over the next 15 years and how that affects the ecosystem. So I'm going to relate that back to the different forms of analytics that we're going to look at. So we'll start by looking back and understanding how a complex system changed based on changing a single variable, reintroduction of wolves, and looking back at it through a video voiceover of the analytical results.
One of the most exciting scientific findings of the past half-century has been the discovery of widespread trophic cascades. A trophic cascade is an ecological process which starts at the top of the food chain and tumbles all the way down to the bottom. And the classic example is what happened in the Yellowstone National Park in the United States when wolves were reintroduced in 1995. Now, we all know that wolves kill various species of animals, but perhaps we're slightly less aware that they give life to many others. Before the wolves turned up, they'd been absent for 70 years, that the numbers of deer, because there was nothing to hunt them, had built up and built up in the Yellowstone Park, and despite efforts by humans to control them, they'd managed to reduce much of the vegetation there to almost nothing. They'd just grazed it away. But as soon as the wolves arrived, even though they were few in number, they started to have the most remarkable effects. First, of course, they killed some of the deer, but that wasn't the major thing. Much more significantly, they radically changed the behavior of the deer. The deer started avoiding certain parts of the park, the places where they could be trapped most easily, particularly the valleys and the gorges. And immediately those places started to regenerate. In some areas, the height of the trees quintupled in just 6 years. Bare valley sides quickly became forests of aspen and willow and cottonwood. And as soon as that happened, the birds started moving in. The number of songbirds, of migratory birds, started to increase greatly. The number of beavers started to increase because beavers like to eat the trees. And beavers, like wolves, are ecosystem engineers. They create niches for other species. And the dams they built in the rivers provided habitats for otters and muskrats and ducks and fish and reptiles and amphibians. The wolves killed coyotes, and as a result of that, the number of rabbits and mice began to rise, which meant more hawks, more weasels, more foxes, more badgers. Ravens and bald eagles came down to feed on the carrion that the wolves had left. Bears fed on it too, and their population began to rise as well, partly also because there were more berries growing on the regenerating shrubs. And the bears reinforced the impact of the wolves by killing some of the calves of the deer. But here's where it gets really interesting. The wolves changed the behavior of the rivers. They began to meander less. There was less erosion. The channels narrowed, more pools formed, more riffle sections, all of which were great for wildlife habitats. The rivers changed in response to the wolves. And the reason was that the regenerating forests stabilized the banks so that they collapsed less often, so that the rivers became more fixed in their course. Similarly, by driving the deer out of some places and the vegetation recovering on the valley sides, there was less soil erosion because the vegetation stabilized that as well. So the wolves, small in number, transform not just the ecosystem of the Yellowstone National Park, this huge area of land, but also its physical geography.
So that was a description of what happened. That's descriptive analytics. And let's look at what the opportunity is maybe for what would have happened if we could have predicted before reintroducing the wolves, what would have happened. I mean, that's a very complex system, but actually all the things that were described in the video were simply single influences. Willows are habitat for Lincoln sparrow, aspen are food for beaver, and so on. And the summer before last, we had a summer intern, and I asked her if she could dig up the report that the video was based on and do some data entry and some analytics around it. And in an afternoon, she picked out all of these influences and mapped them into a graph. This is a tool called a graph database, and Neo4j, which is where I work. And being able to map these out, first of all, there's some power in just being able to visually understand these patterns. But then if you put a query language on top of it, you can actually ask questions like, let's formulate a query for a trophic cascade. If you remember that, that's a process where introducing a predator at the top of the food chain will cause a cycle of change. And so that's the query for trophic cascades. And if you run that query, you get this, starting with wolves down to rivers. And you can see there are 4 inbound relationships to rivers, all of which are promote, which means those are all reinforcing relationships, which means that wolves have to promote rivers. That's what the data is telling us. And therefore, what we've concluded by just looking at this data, none of which was new, none of which was unknown at the time wolves were introduced, we might have been able to predict these effects, which is really powerful. This is the power of predictive analytics, understanding what might happen. And if you can think of the value of being able to predict ahead of time what the introduction of anything will do into any system, whether it's nature or not, then you might decide, well, reintroducing wolves into Yellowstone, probably a good thing. Introducing ferrets into Maui and Hawaii, probably not a good thing. Which we now know, unfortunately, after the fact. And if you map these, this is a slide Babu shared with me ahead of time that I really liked, so I wanted to share it with you as well. If you can see descriptive analytics here and then predictive analytics there, and they're mapped against degree of analytical maturity, so one is more mature than the other, but also business value. Like I said, it's really clear that predictive analytics is much more valuable than descriptive analytics, which of course is itself valuable. And then prescriptive is just taking a relatively small next step, which is let's now apply modeling techniques and try introducing different things or moving different things around. And so it's really predictive analytics, introducing different variables and seeing what will happen. So if you can do the second one, you're probably not too far away from doing the third. Of course, it's going to take hard work and data science and people crunching on numbers, but it's possible. We have the tools and techniques for this. Since we're here at a conference whose title is Big Data and whose topic is Big Data, I thought we could try to start by understanding what is big data really. Let's try to understand it very, very precisely. I love precision, so let's be as precise as possible. And there are a few different ways that I think of big data. When I was preparing for this talk, I kind of had 2 metaphors in mind. One is all of the hordes of data that are stocked up inside the enterprise, and there's lots of gold there. Let's go and find it. And then the other is this oncoming rush, onslaught of, oh my God, there's all this data coming. What do I do with it? So those are hordes and hordes. Another metaphor for big data is, one is finding needles in the haystack. You have all this data, but actually the gold isn't just sitting out there for the taking. You actually have to do a lot of mining and distilling and searching. And so the left represents your alchemical process of distilling and synthesizing, which is trending and aggregation and filtering and sorting. These are a lot of the tools that happen with, say, the whole Hadoop stack of technologies. And then there's finding needles in a haystack, which is finding the outliers and seeing what do those outliers tell us. And then another metaphor that's becoming increasingly important, but I believe that our industry has really, truly overlooked. So I think a lot of there's much more low-hanging fruit here than in the previous areas, is connecting the dots. This is a great image I came across. I missed the attribution on this slide, but I have it again later with the attribution, where you start with data. Data is just all these points. It's not telling me anything. And then I can look through the data and start to color some of those points in different colors. And okay, now it's starting to tell me something. Now it's information. But then how is that data connected? How does this thing relate to this other thing? That's another step. That's knowledge. And then, well, out of those connections, through those connections, maybe I can find some core pieces through the connections that are really valuable. These are the important points that don't stand out until you understand the system and how it's connected. And that's insight. And then lastly is understanding the paths that lead to insight, which is wisdom. And I think this really expresses the opportunity here with data. And if I look at where we are now as an industry, I think we're probably somewhere on the second box or so, just on the verge of starting to make this leap. So of course, as I was preparing for this talk, I thought, well, it's been a while since I've actually looked for a definition of big data. Surely someone's figured it out. So I was enthusiastic about coming in with the one definition to rule them all. And I looked, and I found Gill Press had found 12 big data definitions not too long ago from Forbes. Of course, you can go back to the original Doug Laney 3 Vs when he was at Meta in 2001, and which became Gartner. But then Gartner, Svetlana Sikular, who's still at Gartner, talks about, no, it's not 3 Vs. The big data definition consists of 3 parts. All right, so it's not the 3 Vs. Maybe it's the 4 Vs, so a number of people have tacked on extra Vs, which actually mean different things depending on where we go. And then if you go, if I look at industry, so IBM has 4 Vs, maybe there'll be agreement with an industry, except SAP has not only 4 Vs, but they have 7 definitions of their own. So, okay, this is really not going anywhere. And then someone turned the 4 Vs into 7 Vs. All right, so I give up. But there's some hope still. Someone at the University of Berkeley, Jennifer Dutcher, did a thorough report. This is what we rely on academia for. Thank you, Wayne State. To settle the question once and for all, they interviewed 40 thought leaders across many different industries to come up with the one definition to rule them all. And what they came up with was actually a word cloud, because there were so many different definitions still. So what this tells me is big data probably has something to do with 3 different things. Probably has something to do with technology, but what it's capable of handling. Big is very subjective. Back when I started working with big data, it wasn't called big data, it was called VLDB, very large database. And it just meant something that's too big for the technology of today to easily handle. So we gave it a name, and then that was rebranded big data. So there's something in relationship to what the technology can easily handle. There's the word data in it. So it probably has something to do with data, with its size, with its shape, with how homogeneous or not homogeneous it is, with how predictable it is, how quickly changing. But it's not just about the data, it's still the data in relation to the technology and what it can handle. But most importantly is what you can do with it. So it's new possibilities for doing things with data that create value once a few years ago, I actually did a similar talk on big data, and I added my own fourth V before I realized that everyone was adding their fourth V, and okay, that's undifferentiated. And my fourth V was value, and I said that one's way more important than these other three Vs. Who cares about the other three Vs? It's about value. And so that's sort of my own interpretation, my own takeaway. But my own takeaway isn't actually what's important. What's important for you is what your takeaway is and what big data can mean for you. And that's what this event is about. That's where working together, working with all the folks out here that have booths, working with the startups out here, working with the folks from Wayne State, working with each other from industry. That's where you can collectively come up with a definition and come up with something that's useful for you. Because if it's not useful, who cares what the standard formal definition is? And again, when preparing for this, I thought we have a lot of business people in the audience, and we have a lot of technical folks in the audience. And so I thought it'd be helpful to look from the perspective of the business, what are some of the things you should know about big data? And from the technology perspective, what are some of the things you should know about big data? And again, these aren't comprehensive or carved in stone or anything, but I see these as recurring themes through my work over the last few years. So I wanted to share them. And I'm going to go back to value. This really is the most important thing, is this technology, data analytics, has the opportunity to change the game. So understanding what other companies have done, not only in your industry, but in other industries, is ultra important. I was speaking with a user who was working for oil and gas, and he came out of telco. And in telco, he had a really sophisticated understanding of the network and technologies to manage signal across the network. And so he simply applied that to the oil pipeline, and he was doing things that no one had dreamed before in his industry because he had just taken technology knowledge learned in another industry and applied it. So one nice thing about technology is it can be a bridge between different businesses. And I'm going to pick on a few companies that in the last decade have really been transformative, and ones that you all know. And they all happen to buy into this last connected paradigm that I talked about, that I said and I believe is one of the big opportunities in low-hanging fruit out there. For those of you who were like me in the 90s, Alta Visting around the web and Lycosing around and web crawling around pre-Google, Google was the 36th startup to address this immense problem of trying to index the World Wide Web, which even at that time was getting to be substantially huge. But everyone took the same approach. They all just did a full text index on the body of material, and then rank ordered searches based on full text techniques, which have to do with how many times does a word or a phrase appear in a particular place, and what's the proximity to the words. And it turns out that system is helpful, but Google found a new way to rank order those results. So if you have 100,000 results and you have all these people gaming to be first, who may not actually be the most useful result, but they've gamed the system with their 1-point font, white over white, repeating the word 100 times, then you start to need a better solution. And what Google did is they found a new mechanism for calculating authority, which is based on the number of inbound references from other pages, something called PageRank. And so that algorithm ends up being a very compute-intensive graph algorithm where you need to iterate through, count all the references, and then they end up weighting all the inbound links based on the number of inbound links to that thing. So that's harder to game. So it's iterative. It goes across everything and multiple times. And that completely transformed the industry. And Google also executed in a very smart way and managed to stay ahead. But that was the flipping point for this entire industry, and now they're a dominant force. Another one is Monster to LinkedIn. And basically it's the same thing. You had full text indexing of resumes, full text indexing of job posting, and let's match them. What LinkedIn did was pretty remarkable. Is they not only applied graph techniques to the matching, which would have provided some value, but they also gamified the market, all of us, probably all of you are on LinkedIn, into providing information that wasn't available in digital form, let alone to one company, so that they could then use that and be the single source of truth. And it turns out, this is actually another observation that I didn't quote in that same McKinsey paper, that for certain kinds of industries and use cases, there are compounding network effects where there's more value the more data you have, and LinkedIn is one of those. So through the combination of using connections and the combination of smartly gamifying us into providing our information, they give us value back, and so we give them the value. They were able to disrupt other businesses. And then Amazon, which if any of you in the room aren't, A, excited about using Amazon, but also B, scared to death of Amazon competing with you, then you should be both, actually. They've successfully gone and taken over business, industry after industry after industry, use case after use case, through intelligent analytics. But the first thing that they did in going after the online book business was build very smart recommendation algorithms like collaborative filtering that fired off in real time. And those actually, a smart real-time algorithm for buying generally is something available out of graphs, so they built their own. Okay, so that was point number one, is to understand the differentiation that's possible by looking at your industry and your own and what's happening. Another one, which I really can't emphasize enough, is to work with IT, because in some of the definitions of big data earlier, you were hearing that it's not just about data, it's not just about technology, but these two relate to each other. And the same is true with the opportunity. These things all are interconnected. In order to enable a new business opportunity, you need IT's help to discover what's possible and to look at the lay of the land and the technology and to enable it. Likewise, the reverse is true. IT can go off and up to a certain point, try to pilot and POC new technologies to learn, but until you've been informed by the business as to what direction to go, you can go in a lot of different directions, and it may not be relevant or valuable to your business because of things that only the business knows. And so here I'm talking about building a shared vision with IT that's informed by all those things. And that shared vision is a metaphor, and that metaphor could be something like this. It could be, our vision is we're going to start to use connections more and see what happens with that across, and start small, start in specific areas. Or it might be something like this. It might be we're going to move from batch pre-compute into real time. Like in the Amazon example, if I'm batch pre-computing a recommendation, then maybe for me as a customer who hasn't showed up in 2 days, I'll get good recommendations. But if I've come to the website for the first time today, I'm not going to have a high quality recommendation. I may not come back tomorrow. So it might be about batch to real time, or it might be something else. These are just some examples. And then the third one is to understand the portfolio of information technology that you have at your disposal. And at the highest level, if you're going to understand the portfolio, I would understand this picture. That generally speaking, you have two kinds of systems inside of your company. You have systems of insight, which are used to understand and do predictive analytics and do descriptive analytics and so on. And then you have systems of action, which are the ones at the customer touch point, at the employee touch point, and guess what? At the autonomous device, self-driving car, drone, all these other kinds of things that are just going to start to have autonomy and make their own decisions. And there's a virtuous cycle here between insight being used to drive algorithms that execute in real time, and then the results of the activity coming back and feeding the insight so that I can then refine and create more algorithms, and it's a loop. It just keeps going. And generally speaking, your systems of insight have the quality of being more offline, analytic. It might take a few hours or days or weeks to solve a problem. And it's usually human beings who have training in data analysts, data scientists, to use these systems. And it's things like Hadoop and R and so on. Whereas on the right, it's in the traditional world, your relational database systems, and it's increasingly becoming NoSQL databases and other kinds of more real-time systems. So that's an important picture to keep in mind, because these are the things that you need to be investing in, but you already have invested in, and probably that you can start reaping more value from today. Okay, those are key things for the business to know about big data. Let's look at IT. Key things that IT should know. There are lots of maps that you can find and perspectives on what does the big data landscape look like. And I have some good news for you. What you're not going to have to do is memorize. Oh, I'll show it in a moment, actually. Let me go through the top three. So one is understanding the landscape, how different architectures solve different problems. And there are lots of ways of understanding the landscape, and I'll show you one way that I think is not particularly useful, that overly complicates things. And then I'll show you a few that I think actually are useful. Another one that's really important is technology is not only increasing or not only improving, but its rate of improvement is increasing. Ray Kurzweil writes and talks a lot about this. So however much progress we've made in the last 10 years across all areas of technology, including data, we're going to make the same amount of progress in the next 5 years, and then the following 2.5, and so on. Which means that whatever assumptions you have baked in your head from what you learned 10 years ago, if you use those to design systems today, they're actually probably not right. And this is a hard thing for us to accept as human beings, because we tend to rely on this stable foundation of knowledge and learning in which to operate. But this is not a stable landscape. And if you're going to build a new thing from the ground up today, probably there's been enough evolution in network connectivity, in cloud, in hardware, software, RAM, and so on, that you're going to use not only a new set of technologies to result in incremental improvements, but you might architect things in a completely different way. And one example is, there are lots of examples out there, and I've seen a lot in my own work, of doing XYZ things 1,000 times faster. Well, if you can do something 20% or 50% faster, that's an incremental improvement, and that results in extra efficiency, maybe saving a little money, a little bit of extra revenue. But if I can get from San Francisco to New York, which I did yesterday, in 1,000 times faster than I did yesterday, which was 6 hours, then that completely changes the nature of the game. So anytime you can reach those kinds of improvements, which technology is offering you, then you totally rethink things. And it applies to the business, but it also applies to IT architectures. So question your assumptions, and question them by interacting with the folks here, and by going out and interacting with vendors, with partners, and asking the tough questions. And then the last one is, don't go it alone. And it's actually especially tempting these days. Open source has done a lot of wonderful things. First of all, a lot of innovation has occurred in open source, primarily because this is how small companies go to market with new ideas. And because of innovator's dilemma and just how innovation happens, a lot of innovation comes in that way from small companies. And those small companies are creating new stuff, and oftentimes there's open source and varying models and so on. And the fact that you now have this stuff that you can just download and use, and you don't need to call or talk to anyone, you should go out and do that and use it. But once you get beyond a certain point, you really it becomes counterproductive. You start to spend more money and more time building things if you don't understand how that technology works, than if you actually engage someone, and if you pay systems integrators and vendors and so on. So consider the tech community, consider vendors, and consider the business and the value they can offer in accelerating you. In the same way that you wouldn't start a new Oracle project and not involve data modelers in an Oracle DBA, or DB2 DBA or a Sybase DBA, you shouldn't go out and start your next Hadoop project or Graph project or whatever it might be, key value project, without talking to the person who built the technology or talking to people who are familiar with implementing it. Okay, so now, understanding the landscape. The good news is, don't bother with these. Like this is just gonna crowd your head and leave you confused. So that's the good news. I like to think about this as key solution patterns, and those solution patterns align with technology architecture patterns. So I'm just going to go through a few, again, that I find are useful, and these are mine. So I'd encourage you to develop your own. These are not the only ones. One is the timeliness pattern, and I've talked about this just earlier, that there are certain kinds of processing that can be done in batch and certain kinds of processing that can be done in real time. And when I mentioned the 1000x improvement, there are things that you can do today that you're doing in batch. I guarantee every single person in this room, you have things that you're doing in batch today that could be done in real time if you're using technology that supports that. And what does batch mean? It means that you have these overnight calculations, overnight loading. There's some level of intermittency and latency. There's a gap between the time I brought the data in and you can give an answer. That latency has a cost, and as I mentioned in the recommendations example. There are also certain kinds of batch processing that are useful and necessary to do as batch, but then there are others where it's really not. You're using it as a technology workaround. And I was involved in the past with many systems where in a data warehouse you would pre-compute some sort of treatment score. How am I going to treat this customer the next time I bump into them? And then you would put that score or that action into your relational database, and then the next time the customer shows up at a touch point, then you serve that up. And that's great as a first step. However, if my treatment lags my customer's experience by 8 hours, 24 hours, whenever I ran this calculation, I might be missing a lot. If I'm an airline and I'm interacting with someone as if they had a rosy experience, but they just got bumped off of a flight, guess what? That's the wrong action. So there's actually there's a big value gap or leap in between these two things. So that's an important framework or area to look at. So this is a recommendations example where the recommendations from yesterday, that's useful in some cases, but not in others, including the case where someone's just showed up on the site today for the first time. With real time, you have up to the moment freshness, and then just-in-time processing. And again, the reason you pre-compute everything in Hadoop or in a data warehouse, because Hadoop and data warehouses are not technologies designed for real-time processing. So, what I'm not saying is, I'm not saying use your data warehouses for this, because that's not the right technology. What I am saying is there are new technologies that are on the operational side that are designed to do this. And if I map it back to my insight and action, again, just to repeat myself so that this framework is clear, the batch activity tends to be more over here, and the real-time activity tends to be over here, to generalize. Another framework is the connectedness pattern. This is where if you look at data and how connected is the data and how important is understanding those connections to solving my problem. And if you look at discrete minimally connected data at one end, so this is cases where all I need to do is look up a given piece of information and bring it back, straight lookup. There are lots of problems in your enterprise that just need a straight lookup. You need to keep doing those, and you need technology that's very good at that. And but you probably have a lot of data that is connected, and probably in many of those cases, you're not leveraging those connections. You're not leveraging the fact that your supply chain is 20 levels deep, and if I need to do a food recall, I need to, as fast as possible, find the ingredient, zoom all the way up, zoom all the way out, see what I need to recall. You probably can't do that. It probably takes weeks. In the financial services industry, after Lehman Brothers imploded, it took 2 weeks to unwind and see what all the effects were. If you had that all in a system that understood the connections and allowed you to leverage those, then you can unwind them like that, and you can act on it in a bunch of different ways to mitigate risk, et cetera. And generally, here's how that maps to technology. The original NoSQL use case, actually there were two. It was the DynamoDB paper, which was authored by Amazon, and it was Google Bigtable, both describing problems where they had a discrete single lookup problem that was so volume intensive that the relational databases couldn't handle it, either in terms of actual volume or in terms of cost effectiveness. And they looked at it and said, well, relational databases do a lot of things that aren't necessary to do for this given problem. Relational databases have foreign keys and ACID and constraints. I don't need any of that if all I'm doing is taking a cookie and looking up, bringing back a shopping cart based on that cookie and doing that 1 million times per second. And guess what? The stakes are not that high with a shopping cart. If 1 out of 10,000 shopping carts comes back wrong because I don't have ACID and I have this eventually consistent system, that's not the end of the world. It's not like I have a $3 million wire transfer and 1 out of 10,000 of those can go wrong. That can't happen. You need all of that baggage and overhead in here, like it's super, super critical. And so you have a whole set of systems, namely on the Insight side, the whole Hadoop ecosystem, and on the transactional side, all of NoSQL except for graphs, which is key value, I don't have it here, which is key value document and column family. And then on the connected side, you have graphs. And then relational databases are kind of good at connections, but actually not great. They don't scale that well the more you have, the more hops you have and the denser your connections are. I actually look at join, at connected capability in the relational database as being related to forms, paper forms, which are kind of the original use case that we all learned in school, right? You have an order form and you break it apart and you normalize. Relational databases are great at bringing data together that was forced apart by the normalization rules. So you take your data, you force it apart, you bring it back together. Force it apart, bring it back together. But if I'm trying to do arbitrary analysis, it's not so great. So that's maybe a way to think about these. And so there are some trade-offs with these, which is why you end up with different technologies and why you actually need different technologies. Because if I'm going to lean over here, I'm going to give some things up which might be necessary over here and vice versa. So what do I give up? I give up data model richness in exchange for high volume of data and high volume of transactions. But then I also give up performant insight into connections, because if I've given up connections, I can't spider through and do in-memory pointer chasing and the kinds of techniques that you use if you're leveraging connections. And I give up ACID, where there are a whole bunch of use cases that become instantly useless without ACID. In fact, just 3 weeks ago, Rick Greenwald from Gartner published a report on this talking about how ACID is way more important than you originally thought in the enterprise. So if you're a Gartner subscriber, I would recommend picking that up. And then on the graph side, you sacrifice aggregation. So if I'm going to optimize an architecture to do random arbitrary hops very well, what I'm not going to do as well is large scans through different categories of data and multi-dimensional kinds of aggregation and analysis. It's not as good at that. So you need both. Okay, so I'm going to keep referring back to this. Another set of patterns, so we're talking about patterns, and we talked about timeliness, and then we talked about connectedness. Now I'm going to look at the analytics pattern, which is insight on the left, and then I'm going to look at the action pattern on the right. And let's map these to technologies. If I map out the insight or analytics side, I end up with 4 different things. There's everything around like HDFS, MapReduce, Spark. That's all about storing and aggregating data primarily. And I kind of simplify when I say aggregating. I also mean big sorts and big filters and so on. But that's mostly what it's about, doing that at scale cheaply on commodity machines. And that's an important activity. Another that's becoming increasingly popular is streaming, not having to persist your data, just taking these hordes, the Mongol hordes of data that are coming in, and as they're coming in, doing some aggregation filtering so that I don't need to store every last bit of it because it costs money to store things. The next one is graph computation, being able to do the things I mentioned earlier around understanding the connectedness of your system, but from an analytic perspective, how do my data group into different sorts of clusters and so on. And then machine learning. And these okay, who's using Spark or looking at using Spark in this room? These happen to be the 4 different parts of the Spark stack. So there's Spark SQL, Spark Streaming, GraphX, and which actually we're working with Spark to add Spark Cipher or Cipher over Spark, and then Spark ML. So this is an important thing to understand, and this directly correlates with the stack many of you are using. Okay, let's look on the transactional side. If I look at systems of action, I have transactional databases, which are your primary data systems for supporting systems of action. And I'm ignoring your middleware and virtualization and cloud and other stuff. I'm really focusing on data processing and persistence, which are really at the heart of all of this. You have 5 subpatterns. And I borrowed this from Martin Fowler and a book he wrote called NoSQL Distilled, where he actually talks about how these break out. So one is you have tabular systems, which is RDBMS. Another is you have aggregate-oriented systems that look at discrete data. Really, the only difference between key value, column family, and a document database is what is in your value. So it's a key value, but in a document, a database, you have essentially a JSON structure as your value, and then you index that. So it's a little more sophisticated than just a single property value. And then in column family, you have these, something in between, let's say. And then the last one is graph. So this is how Martin Fowler, who's the inventor of domain-driven design, views these. And this book is a little bit dated, NoSQL Distilled, but I think it's still largely, this is certainly largely valid, and I think a lot of what's in the book is largely valid. Okay, so what can you conclude out of all this? We just looked at like four different insight technologies and 5 different classes of transactional technologies, and we talked about the fact that they all have value and they all have trade-offs. They're all good at certain things but not good at everything. What it means is, the good news for those of you who like to play with technology is you're going to end up using more than one of these in your next solution. The bad news is it's not going to be an easy choice. You're going to need to do some work, but there's a fun exploration to be had. Gardner has a piece from January 15 talking about called the rise of polyglot persistence demands consideration. And what they say is the number of use cases requiring polyglot persistence in order to make critical and timely decisions is rising. And so their advice to CIOs is start planning for systems to involve more than one kind of system. So polyglot persistence simply means heterogeneous data management or database management. Hadoop and HDFS aren't really databases, so database. Okay, I want to give a few examples of this. What can it do for the business? Because at the end of the day, that's the most important thing, right? What is the result? In detecting fraud, a very common and important indispensable pattern is to use discrete analysis for understanding fraud patterns. You map out on some sort of axes. In this case, you have on one axis number of accounts with a bank, and on the other you have revolving debt. And then you look at X number of standard deviations above and below. You draw these nice boundaries, and something that falls out of bounds is viewed as potentially suspicious. And so you investigate it. And this is cases that we've probably all experienced where you go to Aruba and you make a few purchases, and then your credit card company sends you a text or suspends your card. This is important for catching simple, common cases of fraud and theft. Guess what? Fraudsters have gotten very smart. They'll test these boundaries, they'll know exactly where they sit, and then they'll find ways to collude inside of here. That's where connected analysis becomes important. And there's a great paper, I won't call it a great paper, there's a paper, because I co-authored it, so it's not a great paper. It's a paper with a gentleman named Gorka Sadowski exploring 3 different ways in which fraudsters use techniques like this to hide and to siphon off billions of dollars out of the economy. One is in the insurance agency, one's with e-commerce, and one is with first-party bank fraud. And so this is a very common thing, and money laundering is another area where you can do a lot to get your next level of sophistication. Another example from one of our customers, Monsanto, who's spoken a few times, Stampede Con, if any of you go to that, and various other places, where they were able to reduce their product life cycle by an entire year out of a 10-year life cycle, so multi-billion-dollar product development cycle. This is huge impact, and so you can maybe relate this to vehicles or something else with a very long life cycle. They use all sorts of technologies. They use HBase and Spark to do some of the things I mentioned earlier on the insight side. They have Oracle Exadata, Oracle database, and then they're doing the graph analysis with Neo4j. Another example, content findability at Cisco. This is building my Lycos Alta Vista to Google example inside of Cisco. They had a system that salespeople used to search the 30 million documents that Cisco has internally, ranging from PowerPoints to PDFs to SharePoint pages. And a sales rep would spend 30 minutes trying to find the right document. With a sales force of 10,000 people, that's a massive cost to the business. What they do is they take natural language processing techniques, highly parallelize them, take documents in, strip them apart, look for keywords, look for phrases, load those into a graph, and then they use graph-based search along with regular text search, and that reduced the time it took a sales rep to find a document from 30 minutes to less than 3 minutes across a sales force of 10,000. And another example from a large financial institution is they had over 1 billion transactions, financial transactions annually between business parties. And those billion transactions, they wanted to help small businesses understand their relationships with other businesses, but do it from the ground up. Look at the actual transactions, number of transactions, actual dollar amount, and they actually crunched that per month, brought it into the real-time system because another lesson learned is don't try to put every single bit of data into your real-time operational system, your system of action on the right. That's very expensive. So you try to bubble that up and bring just the data that you need in order to be efficient. And so they did that, and that enabled a new project and product. So the takeaways here are understand and classify your problem, what you're trying to do, work with IT, your IT counterpart, work with your business counterpart, and then understand these broad patterns and what other patterns you can come up with that are useful to you, and then use that to map against technologies, and then go try them out, read about them, work with the community, and then once you get to a certain point, actually bring vendors in, bring your systems integrators in. Okay, I'll start to wrap up. Let's talk about what tomorrow will bring. So I'm going to take my wolves change rivers perspective, but I'm going to look at first some history and then some predictive analytics around what might happen inside of the big data landscape. Relational database management systems came about when? They came about during a time where the main business problem that was being solved was digitizing paper forms. You had massive amounts of paper forms. There was a lot of value in taking not only the forms, but the entire business process and digitizing it. And this was done in an era where the hardware technology involved tiny amounts of RAM. That's a Commodore 64 chip. That wasn't that long ago, right? And then where your I/O subsystem had spinning platters with low capacity, sequential I/O, and very low bandwidth between the disk, RAM, and CPU. And that yielded traditional DBMS technology, which is tailored to all those three things. Remember I said technology adapts itself to everything around it, to hardware, to the business problem. If I were to invent a database today, what would it be? Well, one of the important problems that we talked about today in 2017 is the fact that we've solved the paper form problem. That's not a problem anymore. That's been done. That's not undifferentiated. That's well known. What we have is dynamic real-world systems that are rapidly changing, highly interconnected, and there's a lot of value in understanding how those systems interoperate. I need flexible schema. I need rapid understanding of the context and the causality across these systems. RAM is cheap. You can get a terabyte of RAM systems on Amazon now as relatively commoditized hardware. You can get boxes from IBM that have 12 terabytes of physical RAM. That's insane. Most 90% of enterprise data warehouses, according to Gartner, have less than 10 terabytes of data. That means that most of you can put your entire, the majority of data in your entire enterprise in RAM on a single box. And then you're starting to have faster and faster I/O. You have flash. This is flash in a PCIe format, which is much higher bus, higher bandwidth than your standard disk formats. And companies like IBM have technologies like Cappy Flash, which has a coprocessor which does for I/O what a GPU does for graphics. Intel last week announced 3D XPoint, which has somewhere around order of magnitude less latent reads and writes. So it's converging these two things. So if I were to be up here in 2 years, I might have just one thing where you have RAM and I/O, like they will have converged maybe by 2020. So what's the kind of system that I'm going to build? Well, if you look at all the possibilities here and we think outside of the box, dynamic systems, ample, fast, cheap I/O and RAM, I might look to the brain as a model. If I can store my data as nodes and relationships, and if I can process data as through sending currents or signals through the graph and spider through, that actually becomes possible. It's something that was impossible in 1990. You couldn't have done it in a performant way. But it's something that's possible today. And so now we're bringing the kinds of possibilities we have in the human brain to the fore through technologies like graph databases, through technologies like cognitive computing, machine learning, which are nothing more than actually machine learning pipelines are just brain-like graph processing and processes. So this is an area that, as you can probably tell, I'm especially excited about. I've spent my last 5 years working in this area after having spent close to 20 years working in data, mostly with relational databases. I personally believe there's a huge potential here. What are some other people saying? Gartner, in their IT market clock for DBMS systems, says about graph analysis that it's possibly the single most effective competitive differentiator for organizations pursuing data-driven operations and decisions after the design of data capture. What that means is that the single most valuable thing you can do with your data, second to getting it loaded and sourced in the first place, is doing graph analysis. So this is probably worth doing and looking at. Forrester did a market overview for graph databases last year. They're on the verge of refreshing it. And they make some impactful statements too, that in the era of big data, connected data drives business success. And invest in graph databases to succeed in the age of the customer. So if I look forward, this is one of the areas that I think is just starting to get the elbow of the curve and really starting to take off. Recap. First of all, don't worry about definitions. Create your own. Everyone's trying to figure this stuff out, and it's moving really fast anyway. So work together, socialize, connect, and just create and take what's useful. And if you find something that's not useful, just discard it or put it on the back burner. Next, use what you learn about technology possibilities to enable the business, and use what you learn about business possibilities to challenge technology and to challenge IT. So work together. Most failed IT projects fail because business and IT aren't working together. And then lastly, okay, you saw my fraud detection picture. Gardner has a great quote saying, don't consider traditional technology adequate to keep up with criminal trends. I'm going to modify that and say, don't consider traditional technology adequate to keep up with the world. Look at the new stuff. This is what today is about. So connect, and thank you.
I'll say wow again, eh? You said something at the end here, Phil, about the things changing and how quickly they change. That's one of the reasons why we have the startup group here, and so we encourage people to look at the startups, because this is going to be where you're going to see some of the leading stuff that maybe we'll have at our next symposium. Thank you all.